Hi everyone, my name is Sakshyam Ghimire and I'm an undergrad in polymer science and engineering at University of Southern Mississippi. Today I'm presenting a solution for one of the most persistent uh, pollutants in our ocean, expanded polystyrene or EPS, maritime infrastructure. We're not trying to substitute it with other material but trying to re-engineer the entire infrastructure of how marine buoys are built. We are trying to make a marine-degradable structural foam buoys and mitigating the microplastic pollution through biopolymer architecture. And the biopolymer that we've chosen is polyhydroxyalkanates, PHA. Current commercial maritime infrastructure relies heavily on EPS foam, and why would they not, since EPS is cheap and highly buoyant? The problem, however, is the mechanical aspect of EPS. It is a gigantic structural failure in high-impact marine environment, which is how the ocean usually is. When it crashes against docks, boat hulls, or steel winches, it undergoes catastrophic brittle failure. It doesn't just break but shatter into millions of unrecoverable microplastic bits. Research by Jantos and Walker demonstrate that there are fragments are accumulating in the marine column with sweeping legislative bans on EPS flow that are already taking place. For example, in Washington and South Korea, there are already legislative bans on EPS. The fishing and aquaculture industries are desperate for a pivot, and that's why we are suggesting using polyhydroxyalkanates. Our solution is using PHA, polyhydroxyalkanates. Unlike traditional petroleum-based plastic, PHA is biologically synthesized and natively marine degradable. Looking at the biological carbon cycle on this slide, we can see the mechanism. When submerged, ubiquitous marine bacterioplankton recognize the PHA polymer backbone as carbon food source. They secrete depolymerize enzymes that actively metabolize the plastic into biomass and carbon dioxide. This is not just passive for degradation or fragmentation. The material is literally being eaten by the ocean. But raw PHA is heavy and expensive. To make it commercially viable for buoyancy application, we have to foam it. To achieve that, we utilize supercritical carbon dioxide continuous co-extrusion. Looking at the SEM micrograph from Chang's et al. Research, we can see a successfully engineered closed cell matrix. This extension is critical for marine application. Because the cells are closed, each microscopic bubble is an independent sealed pocket of gas. If a boat propeller slashes the buoy, it won't float and sink. The core remains entirely watertight. This provides a massive safety and reliability upgrade over the hollow plastic cells that are dominating the market currently. Of course, foaming a polymer naturally reduces its mechanical strength. But to counter this, our processing relies on an M&M architecture profile, a high dense solid outer skin protecting a microcellular foam core. In the figure from the Eval and Scardino paper, we map the ratio of plastic stress over relative density. Most conventional foam immediately lose all structural integrity as they got lighter. But by maintaining the solid outer skin during extrusion cooling phase, we stay in the upper threshold of the stress curve. That means we achieve the high blunt force resistance of a solid plastic buoy while also having extreme buoyancy and lightweight profile of a EPS buoy, foam buoy. The ultimate proof of concept lies in its end life behavior. If the structural buoy, for example, breaks free from a mooring line and is lost at sea, it doesn't just become a ghost pollutant. The kinetic degradation from Arias et al. Validates our matrix. Looking at the curve APS VB, it's a common commercial PHA blend. It reaches over 80% biodegradation in raw seawater in under 200 days, while EPS4 would persist in water column for centuries choking marine life. Our structural foam buoy is safely and completely metabolized back in the ecosystem in less than a year. It doesn't take a engineer or a businessman to know the biggest problem or barrier in to adopt the biopolymer is its cost. The good news is our economics are good. The current legal replacement for EPS floats is SDP cells, high density polyethylene cells that cost roughly about $60 minimum in wholesale. But by using supercritical carbon dioxide to form 80% of our PHA mass, we project a cost of about $50 per unit. But the real savings are operational. The- What I mean by that is when SDP breaks it, the sovereign retrieval fee you have to pay, and another heavy landfill cost that you have to pay to mitigate it legally. But when PHA is lost, it safely degrades in the ocean, so you will not be paying any retrieval fee, neither any landfill cost. It eliminates the entire liability. There we have it. There is an imminent ban coming in the EPS forms sooner or later, and it will disrupt the whole fishing industries. SDPE sales are too expensive for farmers or aquaculture industry to use. That's why that was the main reason for doing this whole research and figuring out an alternative for that. So the bottom line here now is we eliminating microplastic through using advanced structural foam engineering. So we have to adapt with this because again, there is a ban incoming and it is coming 100%. Thank you for your time. I'm Sakshyam Ghimire. I apologize. I recorded this in multiple fractions. I am not really good at interpreting this. I invite any questions though.